So good afternoon everyone. My name's James Mitchell. I'm a Principal Software Engineer at Sledgehammer Games, Melbourne, and I'm going to be talking about building more efficient locks today. So let's dive straight into it. So what I'm going to talk about is what makes a good lock, why do we need locks, and then iteratively building a lock. So in this I'll sort of cover some cache coherence considerations, out-of-order execution, memory ordering, the operating system scheduler, and then trying to get the memory usage down. This talk contains a lot of code, it does, so if you're sitting up the back, it might be better to sort of move up the front. I've tried to keep everything with fairly big font though. And I'll also use the words lock and mutex interchangeably, so if you feel I'm using the wrong word for it, just assume that I said the other one. So, first up, what makes a good lock? So ideally you want fine-grained locks. So instead of having, say, a lock for an AI system, you might want locks for every individual actor within the AI system. So this means that when you acquire a lock for something, you're not competing with a lot of other threads that potentially want that same lock. And then in order to do this, we really want a low memory footprint. Ideally, we want sort of 1 byte or even just a few bits for a lock. And we also want zero initialization, so when that lock is created, we don't want to do a bunch of complex initialization. That way we can have thousands or tens of thousands of locks potentially. We also want to optimize for the uncontended case. So we're really looking at the situation where we want nothing else contending on those locks, and when there is contention, we probably want to investigate that contention and reduce the contention rather than trying to optimize for the contention itself. So, why do we need locks? So here we've got a small little example where we've got thread 1 that's attempting to add an item to a list, and thread 2 that's attempting to remove an item from that same list. We'll assume that these aren't the same item. These operations, while they just look like a single function call, there's typically more going on in the background. The code here is not really that important, but what's important is that we've often got a lot of shared data within these. So here we've got sort of a data and a size variable that's contained within that list, and those can be accessed at the same time in both threads if they were both to execute simultaneously. And that could cause a race condition. We could get corrupted data. We could get either the add occurs or the remove occurs and the other one doesn't occur. So this is where we can use mutexes, and we can sort of lock that data in the list using a mutex. So we sort of acquire the mutex up front using sort of a lock function on that, and then we unlock it after we've done whatever we need. And this prevents 2 threads from running at once. So let's look at a very basic initial implementation of a mutex. So here we've got a while loop. It's got a state variable there. That state variable is either a 1 or a 0, where 0 indicates that it's not currently locked and 1 indicates that it is locked. And then in this while loop, what we do is we first off attempt to do an exchange for 1. So exchanging that we've locked it. If that comes back as a 0 after we did the exchange, then it was already unlocked, in which case we don't do the loop. But if it did come back as a 1, then it means it was already locked. So let's sort of do that first step. And so thread 1 managed to acquire that lock, it did. So it did the initial exchange, it got back the 0 for its exchange, and it's able to start doing the adding to the list, while thread 2 is just going to sit here and spin. And then once thread 1 has finished doing what it's doing, and it goes to unlock the mutex, then it's going to store into the state a 0. Then when thread 2 attempts to do its exchange, then it's going to see the 0 there for that exchange, and it's going to be able to execute its code. So that prevented those 2 threads from executing on that same list at the same time. So with this naive implementation, there's some cache coherence considerations that we might want to do. So take a little bit of a detour and get a better understanding of that. So typically everything sort of lives in memory for these mutexes, but memory from the view of sort of the CPU and different caches doesn't work as a whole memory block. Instead, things get broken down into cache lines. These cache lines are typically 64 bytes in length, they are. And there's a protocol that gets used for synchronizing these different caches. There's typically multiple levels of caches, so you might have sort of a different cache on each CPU core There might even be one or two of those. They might be split between data and instruction caches, and then you might have shared caches, and all of them have sort of different views of memory. So there's a bunch of different protocols that are used. Sort of more simplified and basic protocol for understanding these is the MESI protocol, or modified, exclusive, shared, and invalid. So every cache line is in one of those specific states. If the cache line doesn't exist in that CPU cache, it's assumed to be invalid. So let's step through and take a look at how some of those states work. So let's say that core 0, or a thread on core 0, wants to read from memory address 50. So what's going to happen is that the cache line that contains that data, not just the specific data that's read, but the cache line that contains that data, will be sent over from main memory and stored on that CPU cache. It'll appear as an exclusive state. So this means that no other CPU cache has a copy of that data. That being in an exclusive state means it's really quick for then the CPU or the cache to switch into a modified state. So let's say that that same core wants to again write to that same address, and then it'll move from an exclusive state to a modified state. Now, if another CPU core wants to read from that same address, what ends up happening is the CPU core that's got it in the modified state then needs to send it over to the other CPU core, and it'll change it into a shared state because it now exists in multiple different CPU cores. And then if core 2 wants to write to another address within that same cache line, then it's going to have to tell the first core to invalidate its cache, and it's going to move it into a modified state. And then if core 0 wants to read from the same thing it was just reading from earlier, then core 2 is going to send it over to core 0. So it sort of gets this back and forth whenever we're doing modifying and reading of data. And they're in a shared state, and then if the core 1 wants to also access something on that same cache line, it's not even the same address, it's accessing address 60, it's going to also get sort of that shared state of the data. So let's have a look at how that might play out with that initial mutex that we had implemented. So assuming that the data that we had was just a pointer, and that's taking up 8 bytes, then we've got the size that was taking up, let's just say 4 bytes there, and then the mutex itself, which is just that 0 or 1 state variable. We'll assume that it was 4 bytes. All of that fits in one cache line. It does. So let's see how that might play out with our mutex. We'll assume that they're just in a shared state initially, just to dig into this. So they're both able to read from that same cache line, but when thread 2, while it's doing this sort of checking whether it can acquire the mutex, it's doing this exchange, it's actually modifying that variable. Even though it hasn't changed it from the existing state of being locked, it's still issuing a modification sort of request for that cache line. It is, and what we've caused is the cache line that exists on core 1 to also be invalidated. So that means that when core 1 wants to attempt to read that data, it needs to go back. It's going to request it, core 2 is going to send it over, and then they're both in a shared state. So it's sort of constantly doing this sort of modification and invalidation of the data within core 1. And core 1's the one doing the main bit of work. Core 2 is just sitting there spinning. So because we've got this loop of exchange, we're slowing down core 1's work because it's constantly, every time it goes to touch the memory in the list, we're just killing it with the other core. We are sort of going back and forth between shared and modified. So one way in which we can sort of address this sort of invalidation that's happening from core 2 is, instead of doing just the exchange and then looping with it, when the exchange failed and it was already locked, if instead we do a loop that ends up doing just a load, so we're just checking whether it's still locked. And if it was still locked, then we just keep doing that. So this means that it's not going to end up in that modified state. It isn't. So instead it's going to just only be in the shared state. We'll still potentially cause the thread 1 on core 1 to change its modified state potentially into a shared state, but we're doing less invalidation of the work that thread 1's attempting to do. So anyone that's a little bit sort of familiar with atomic variables might be thinking that potentially we could be able to use a compare and exchange instruction or operation. So these are where you do a sort of, it does a check to see what the variable is, and then it only changes that variable if it matches it. So we're doing sort of a compare and exchange. If it was unlocked, then we store it as locked, and then if that succeeded, then we sort of exit out of that loop. So that unfortunately won't sort of address this problem, because compare and exchange still ends up forcing the sort of CPU cache line to be moved into a modified state, even though it didn't modify that variable. So that's where that loop's really helpful for addressing that, that cache contention that we were getting. So another thing that we need to consider is out of order execution. So if we look back at this loop, so when there is that contention, the main part of this other thread is just sitting here in this loop. So we'll dig into the impact that it might have with out of order execution. So first off, let's sort of look at what that might generate in terms of sort of CPU instructions. This is just a generic sort of assumption of sort of the assembly that it might generate. So what we're doing is sort of loading for that state variable. We're loading it into a register. We do a comparison on that variable and compare it with 0 just to check whether it was unlocked or not. That's going to set some flags, and then we do a jump depending on what those flags are. So we jump back to that sort of spin loop. So the CPU is going to sort of see this loop, it is, and it's going to predict that that branch is happening, because we're just assuming that we're doing this loop again and again, because we're doing it as fast as what the CPU will allow us, and as fast as it can sort of get that memory going. So the CPU doesn't do these instructions one by one. What it can do is it can start doing things out of order, and it can start sort of predicting what it's attempting to do. So part of this, you might be thinking, oh yeah, there's only that one register there for it to deal with. What instead happens is the CPU has multiple different sort of registers. It'll rename those registers into different versions. So here's just an example here of where what register renaming might have ended up with, where it's got sort of that load, does the flags. It might have even combined the setting of those flags and the comparison with the jump itself. So then it's sort of just one operation that it's doing. And because it's predicting that it's going to do that next loop, it's essentially going to do it again and again and keep doing this as fast as it can. So while it's doing these, it's actually using execution units on the CPU core. It is. So let's take a little bit of a look at the first loop of this, where we're using sort of, they've got assumption of sort of 3 execution units within this hypothetical CPU core, where there's a load execution unit and then 2 ALU execution units. And for the code that we're looking at, it's really just using the load execution unit there to do a load from the state variable, and then the ALU is just doing that comparison operation. So because the load might potentially take time, it's going to, in this example, say on cycle 1 we're going to issue the load, and it's not until cycle 6 that we actually get that comparison of the data that it managed to load out. So what the CPU can do, because it doesn't depend on any of those, it's going to predict that it's still taking those branches, is it's going to start sort of speculative doing each of those loads each time, and it's going to sort of start filling up sort of the ALU with a bunch of stuff. And we've ended up here doing sort of essentially 6 loads before we do the first comparison of the flag, and the first comparison to see whether it was unlocked or not. So all of those loads that were speculated are sort of filling up the CPU core's execution units in both the load and the ALU. And when we're using sort of hyperthreading or multiple sort of logical CPU cores on a single physical CPU, then we're stealing resources away from potentially another CPU core that's on that same physical CPU core. And this can have a fairly significant impact depending on what the other CPU core is doing. But one thing in which this also sort of shows up is what happens when we hit that sort of state where it reads back that the lock was unlocked. So let's say that the one that happened in cycle 4, which stores in register the third version of that register, reads back that it was unlocked. So we end up checking that down in cycle 9, we do, and it's going to mispredict that occurred. So what the CPU needs to do is we did all of this work, we guessed that we were going to have to do more loads, we guessed that we were going to have to do more flag comparisons, is all of this extra work that we did needs to be thrown away, and it needs to redo what it had previously should have done, which was actually acquire the lock at that point in time. And this sort of branch misprediction, when we've got a bunch of stuff to discard, can be reasonably expensive. So one thing that we can do to sort of prevent some of that sort of speculative loading and all of those operations is, instead of doing sort of this continue where it's just as quick a loop as possible, is instead if we sort of start using what exists on a lot of CPU architectures, which is sort of a pause instruction. That prevents some of that sort of speculative loading from occurring. It doesn't necessarily prevent the branch prediction, but the branch mispredicting, but it'll mean that there's less stuff for it to discard. There's less sort of impact on the other CPU cores. It is. So the pause instruction, unfortunately, isn't always consistent in how long it is. It depends on how big the CPU pipeline is for different CPU architectures. Sometimes they might be even sort of 100 cycles. Sometimes they might even be just a dozen cycles. So some CPU architectures include ways of waiting on a memory address. So we can sort of, on Intel, you've got wait instructions that sort of you specify a memory address or essentially a cache line that's going to wait on, and you wait on that for a specific period of time, and it'll enter a lower power state when it's doing that, so it's not stealing away from extra resources which another CPU core could be using. Unfortunately, it's Intel specific, that one. AMD's got their own version, which is mmonitorx, and then if you're working with ARM, there's other versions of it that exist. But if you're building your own mutexes, I'll leave you to dig into the specifics of all of those different variants if you're looking at using those. So another thing that we need to consider is memory ordering. So on a CPU, when there's multiple sort of threads running, the CPU and the compiler are both able to reorder your reads and your writes. So let's assume that we've got sort of A, B, and C here. They're not atomic variables, they're just normal variables that exist in memory. And we're just storing into A1, B2, and C3. We're doing all of these stores, and then in thread 2, we assume that if C managed to get set to 3, that both A and B are set to 1 and 2. So you might assume we've written those all in a specific order. We're working with, say, x86, and everyone says that it's strongly ordered, that none of that will be reordered. Unfortunately, the compiler can reorder it, and also the CPU could potentially end up reordering things depending on the different situations. So what could happen is that store to C that we were depending on to assume that A and B had already been set, it could end up being moved up before the store to B. And that would mean that those asserts that we had on the other side for thread 2 would fail. So one way in which we can address this is if, instead of doing these sort of raw reads and writes to standard variables, is we start turning those into atomics. So we'll just assume here that load and store here just means that it's doing an atomic read and write for these variables. Atomics come in many sort of different variations, and they, depending on sort of the language that you're using and the different architecture, they might have different ordering requirements. So here we're going to sort of assume that this is C++, which means that it's sort of memory order sequentially consistent. And what that sort of means is that all sequentially consistent operations have a sort of an order that exists. So A will always occur before B, B will always occur before C in this example. And it also means that any variables that are around those won't move below them. So because we only had C that we were really depending on here for this check, what we could end up doing is just changing C to be an atomic variable. So if C was an atomic variable, then it doesn't matter if A and B get reordered, because we're just doing that sort of store into C as an atomic, and doing it as a sequentially consistent atomic. So that means that neither A or B, those stores, can move down below it, and C can't move up. And the same can happen with that load, where only the load for A and B must happen after the load from C. So this is perfectly safe. But sequentially consistent loads can be fairly expensive depending on the CPU architecture. So with those cases that I showed before, there's other more complex things like store buffers that exist that sometimes those need to be flushed, or they're not quite flushed, but let's just assume they sort of get flushed every time you do that that sequentially consistent store. And the same with a load, where sometimes there can be sort of a queue of sort of an invalidation queue that could happen with that load. Depends on the CPU that you're using, whether it's sort of a stronger memory model or a weaker one, then the cost of these might vary. So what we can instead do is use something that's a little bit more sort of constrained for the situation that we're after, which is using memory order acquire and release. So with memory order acquire and release, instead of it preventing anything from moving above or below them, with memory order release, it prevents anything that's above it, so that A and B, from moving down below it. But it allows for anything below that, so there's this extra store to D, to be moved up above it. So this prevents the need for sort of those store buffer flushes and things like that. So it's a little bit more lightweight operation. And on the other end, we've got sort of this memory order acquire that happens on the same atomic variable. You can't use these with different atomic variables and then assume that they're going to synchronize. They really need to be the same variable, which is C in the case that we've got here. So that memory order acquire, it allows for things that are above that memory order acquire to move below them. In this case, it probably wouldn't move into the if itself, but it could move it after it's done that load to C. So yeah, the acquire and release allow that synchronization to occur within things. So let's see how we might potentially apply this to our mutex. So if we go back to where we had before, these atomic operations. So with a mutex, we typically don't want anything inside of that mutex to move outside of it. So in order to do the lock, we sort of want to acquire the data, so we want to make certain that anything that's inside that mutex area doesn't move out of it. So we're only ever doing it whenever the lock was acquired. Then everything below that must work with essentially a new chunk of a new view of that memory. For when we didn't manage to acquire that lock, we're just doing a relax, because that load there, nothing else sort of needs to be ordered around it. Where the unlock, we just want to prevent anything that was inside the mutex from moving outside of it. So that's where we do a memory order release for it instead. Unfortunately, these sort of memory order release and acquire, they take up quite a bit of slide room, so I'm not going to include them in the rest of the slides where I'm showing atomic variables. I'll leave it up to you guys to sort of dig into and understand those better in the situations where you might need to use them. So another thing that we also need to consider when we're working with building mutexes is the operating system scheduler. So it might be nice and helpful to assume that when you have a thread that runs, that it just gets pure control over a CPU core, but often there's multiple different threads. There might be thousands of threads that are running on an individual machine, and you might only have 16 cores for things to run on. So what the CPU does is it sort of divides up time in between different threads that are wanting to run. And these are divided up into time slices. So let's assume that thread 1 here was running, it acquired a mutex, and then its time slice ended. So what the CPU scheduler is going to do is it's going to look for another thread to run. Let's say we had another thread that was also wanting to acquire a mutex. It begins running, it starts to do the mutex lock, it ends up with that exchange failing, and it's just going to sit it there and do the load, because thread 1's not running. We've stopped thread 1 completely because we're doing all the work with thread 2. So this will spin all the way up until it's sort of ended its time slice, or something else has caused it to get interrupted. So an approach to addressing this is to instead tell the operating system, when we're doing this loop, instead of doing a pause, we want to yield out and allow other threads to run. So this sort of thread yield approach will typically allow another thread that's sort of assigned to that CPU core to be able to execute, but thread yield is not sort of the same on all operating systems. Sometimes it might allow things that are the same priority to run or higher priority. Other times it might only sort of might allow for lower priority threads to run. And we might also just be doing this sort of thread yield on a CPU core that didn't have the other thread that was holding the mutex. So we've just given up our time slice, and the other thread might have ended up unlocking the mutex straight away. But when the thread yields there, at least if they're on the same CPU core, then it's going to end that time slice and allow the other thread to run and unlock. So it doesn't always save all the situations, but it's a little bit better than the pause instruction at times. So what we can do instead of another approach is we can use what's sort of called an atomic wait and atomic sort of notify, or for anyone that's sort of familiar with POSIX, futexes or fast user mode mutexes, where you sort of wait on a specific address or an atomic variable, and you wait on it expecting it to be in a specific state. In this case, we're expecting it to be 1, so we expect that it's already locked. We do, and the thread will actually go to sleep while ever it's in that state. It adds it to a queue, and then it checks that state. And then it doesn't actually monitor that memory address. It's only sort of adding it to a queue, then checking it after it's added to a queue. And then in the unlock version of this, we sort of do our normal unlock, and then we're just notifying for other threads to be, for one of those threads to be woken up, so then it can continue. Unfortunately, these are system calls, and we probably don't want to be doing that sort of notify one every time that we're doing the unlock, because system calls are very expensive. They are. So what we potentially want to do is add in there sort of a little bit of extra state to indicate whether we need to do that notify one. So what we'll do is use 2 bits instead for our mutex. So we've got sort of that locked bit, which is similar to the 1 and 0 that we were using before. And now we're going to do sort of a compare and exchange. So we're sort of doing a compare and exchange. We're expecting it to be 0. So by default, when we go to acquire a lock, we expect no one else is locking it, because that's our common case. And we'll store the locked bit if that did succeed. If that happened, we just exit out. If it didn't happen, then we're going to enter in this loop. And this loop's only for when there is contention, so when there is another thread that already has acquired that lock. And we're going to check the expected state to see whether it did have the locked bit set. If the locked bit wasn't set, then we're going to end up doing another compare and exchange, and we'll just attempt to set that locked bit. So there's this has parked bit that's been added in here. So this comparison here, where we're doing that compare and exchange and still keeping the parked bit, it allows for barging. So barging means that if another thread comes in and the lock is unlocked, then we'll just grab it straight away. We don't care what order in which mutexes are acquired. So if you've got, say, 10 different threads that are all attempting to acquire a mutex, the one in which sort of they don't always acquire that lock in the same order. It could just be the one that just acquired it and then released it and wanted to acquire it again. That's the one that actually managed to acquire it. This has some benefits of sort of allowing for greater throughput for that mutex, but it does mean that we're potentially starving out some of those other threads. And because we're designing these mutexes with sort of the ideal of we don't want contention, and anytime we do get contention, we want to address that, we don't really care much about sort of trying to prevent the starvation happening for other threads. So barging's the more ideal situation for that. So that's that first sort of compare and exchange. The second compare and exchange. The third compare and exchange, where we're adding this has parked flag. You might be thinking, why don't we add that flag with sort of an atomic or something like that? If we do it with an atomic or, then we're potentially setting it even in a situation where that lock, it might have been unlocked in between that first comparison and the second one, where compare and exchange, that can fail if we need, and it's not going to set that parked bit in that situation. We could add a condition here to check whether it already has parked, but that's not really too important for us, and it would add too much room to the slides. And then we're only going to wait in the situation where the locked bit was set and the has parked bit was set. So that's the only time in which we'll end up entering that sort of atomic weight. If either of those got unset, then we go back to that loop and we keep trying again. So for the unlock, we're just doing an exchange of the existing value that was there. So we're just storing in unlocked, and we get back the old value of it, and we check whether the has parked flag, so that means that something else is waiting there. And then we notify all threads. We can't really do a notify one because we don't have that sort of state there. So this is sort of a very basic way of doing this, and hopefully you don't have many things waiting on it, that when you do a notify all that you're doing a lot of waking of different threads. If you do, then there's probably a little bit too much contention. So one of the unfortunate things about this atomic wait and notify is that if you're using C++ at least, they're not available till C++ 20, and they also don't exist on all platforms. So what we can instead do is we move to having a operating system mutex inside of our mutex, just to complicate things a little bit more. And we use a mutex and a condition variable to start waking up threads. So condition variables allow for sort of waiting on a specific state to checking whether a specific state exists, and then we put the thread to sleep on that condition variable. And then for when we want to wake it up, we sort of do the same and notify that thread to wake up. There's more optimal ways of sort of doing this mutex and condition variable here, but it's just a very basic example of how we can do this implementation for something where we don't have atomic wait and atomic notify. But because we've done this, we've potentially sort of blown out the instance of that mutex. So that mutex, because the operating system mutex and condition variable, some of those combined together can end up well over 100 bytes, and that's not our 1 byte optimal situation. So in order to sort of cut down memory usage, let's break out and implement our own atomic wait and atomic notify functions. So we'll start out by replacing those. We've just got the same as the normal one, the other ones from the other slide. Let's step into an implementation of it. So takes in the atomic variable or an address to that atomic variable, and then it has the old value, or the value that it expects it to still be in. We acquire just a global mutex, we do. Remember, this mutex is only acquired when there is contention. So potentially there's extra contention of two different threads that might want to acquire this same mutex, but it should be fairly short-lived. Then we do a hash map lookup for that atomic variable. We might need to insert it into that hash map, but I've sort of kept this short just to keep it simple. And so we're acquiring sort of this element that exists just for that one atomic variable, and that element is just the condition variable at this point in time. And we check the atomic after sort of we've got that. We just want to verify that it is there, and we're only doing that while we've got that other mutex acquired, because it's sort of creating this little thing that we've got ordering on. It does. And then we wait on that condition variable just using that global mutex. And then notify all, again, we just look up the atomic, and then we notify all. We could potentially sort of clean up and remove the item from this hash map so we don't end up blowing things out. So there's a lot of little optimizations that you could do in an implementation like this, but it is just a quick little overview. So some of these sort of lead to implementations that get close to a parking lot that I'll cover a little bit later. So that notify all was sort of something that I mentioned before that we might not want to do for high contention cases. So we might want to introduce sort of a notify one. So what we can do is just on that same atomic variable, if we just track a count of how many things are parked on that variable. So in atomic wait, we just increment a counter. When we do a notify all, we're just resetting that counter. And then in the notify one, we just decrement that, and then we're adding in a callback in here, and we're doing that under the lock because we want to be able to know when we should remove that flag, which I'll show in the next slide on how we sort of make use of that callback. And all of that sort of happens under the mutex that is the global mutex that we've got. So that means that none of these are really atomic variables that we're working with, and we only have that sort of check for the count at the same time as we know whether the queue was empty or not for that specific atomic weight and notify. So to see how we might sort of make use of that for our mutex, we would do sort of a compare and exchange now instead. So we're assuming that it's only locked. When doing that unlocked, we don't assume that anything's parked because contention's not the goal that we're after. And if it did manage to do that sort of compare and exchange and storing that it's unlocked, then we return back out. Otherwise, we're going to notify one thread. We're going to pass in that sort of state variable that we're waiting and notifying on. And then we've got that callback that occurs under the mutex, and we store back into our state the whether it has parked or not. So these are essentially unsetting that locked bit, and we're only setting the parked bit depending on if there is potentially more threads that might need to be woken up later. So this is sort of an extremely basic mutex implementation that's sort of using those atomic wait and notify. So one thing that we've got is we've got a lot of code here that only occurs when there is contention. And we want to keep our locks really simple, and we're after that sort of uncontended case to be our main goal. So what we can do is if we grab all of this code, let's move it out into its own function, and we only ever do that when the compare and exchange fails. So for these locks, for our uncontended case, we've hopefully just got a single instruction of compare and exchange that occurs, and then just a branch to call out to a function when it does need to sort of do that slow path and work with that hash map. So this should be able to be inlined in a lot of cases, it should, and it'll mean we don't have function call overheads and all of that except for the situation where we do actually need it. So one of the things for anyone that's dealt with atomics a little bit might realise that there's not just one version of compare and exchange. There's typically two different versions of compare and exchange that exist. So these are sort of compare and exchange weak and compare and exchange strong. So with the weak version of compare and exchange, it can fail even in the situation where the value that we were comparing it with was the exact value that we were checking. So for that unlock, it could fail to do the compare and exchange even if it didn't have the has parked bit. So those failures can occur potentially because something else in the same cache line had changed. It could occur because something even in the same page could have changed, or something in the whole memory space. So it depends on the CPU and just how it wants to sort of deal with some of those failures. There could also be a bunch of other conditions that could cause the failures to occur. The thread might sort of get suspended or something like that within there. These failures typically only occur in sort of some older memory sort of model CPUs. A lot of them compare and exchange weak and strong are exactly the same thing, but we typically want to sort of use the weaker version if we're doing something within a loop. We do, so if we've got a compare and exchange that's occurring with a loop, then we might use the weaker version because we're constantly checking that value. The compare and exchange strong, it doesn't have those same failures, so it'll only fail the compare and exchange if the value didn't match what was there. We typically use these in situations where we might not have a loop or a check afterwards for what the variable is. On architectures which sort of use the load link or store conditional version of atomics, the compiler will typically generate a loop whenever you use a compare and exchange strong that is just a loop of compare and exchange weak. So these can have a little bit of an overhead depending on the CPU that's used. Modern mobile sort of architectures like ARM 8.1 and above sort of don't have this issue, but if you're using something earlier, then you might be compiling with sort of these load link and store conditional. So to look at just an example of how we might potentially use those within our mutex, because our lock, we end up doing sort of a check straight afterwards in that sort of slow path, we might want to just do a compare and exchange weak there, so that way it's not doing that, introducing a loop in that situation. And then for the unlock, we might want sort of more the stronger version because we end up doing the hash map and everything. We don't check the value again afterwards. So these are sort of an example where you might use it possibly in this situation. Both of them being strong might be the more ideal thing. So it's a case-by-case basis and really sort of looking at how you want to use those mutexes. So we've built out sort of this these atomic wait and notify functions, can we potentially use them for other things? So one thing in which we can do for that is we could modify our atomic wait to, instead of having that sort of check for what the variable was already set to, which we were checking is locked and has parked, we can instead have a validation function. And this validation function is sort of stepping closer to a parking lot implementation. And because we've got that sort of validation function, we can implement our own condition variable now. So for a wait on a condition variable, so if we've introduced our mutex, let's introduce a condition variable to be used with that mutex. So when we do the wait, instead of having that sort of variable that it waits on, we're just always going to wait for the condition variable. And we typically pass in a mutex into a condition variable, or we always pass in a mutex into a condition variable wait. What we're going to do is store that there is has waiters, so that's just a Boolean variable that we've got in our condition variable. So we set that to true, and then we unlock the mutex, and we return true because we've put that thread to sleep. And then in the notify one, we're checking whether there's any waiters. If there wasn't any waiters, then we're not going to attempt to do anything. Otherwise, we'll do an atomic notify, and we're using that same callback and only setting the has waiters based on whether there's any more things within that queue, so whether that park count was 0 or not. So that's a very basic condition variable that we can implement using the same things. And we can implement lots of synchronization primitives using this same atomic wait and notify. We can implement events, we can implement semaphores, we can build a lot of different things out, and we can sort of get them really down to a couple of bytes of what we want. The other thing that we can do is, with the atomic wait and notify, those are our real contention areas. So this is where we can add in the profile markers into those and start tracking things. You can track extra debug data that you want to do of how often things are contending. But we've kept that main lock down to essentially 1 byte and just a compare and exchange for lock and unlock, and everything's hidden behind our atomic wait and notify. So that's it for the implementation of mutexes. There is typically, for a parking lot implementation, there is more to it, where instead of doing it sort of just waiting on that address, you might have sort of the condition variable and mutex be associated with the thread itself. So it might be a thread local, it might sort of be a hash map that it looks up for different threads, might even just be a mutex and condition variable that only gets created when it does the waiting. So there's many different ways in which they can be implemented, but it's a basic version just to keep the slides sort of simple, so people get sort of a good understanding of the atomic waiting and notifying and what a parking lot really is, which is that sort of waiting on something with a condition instead of waiting on it with whatever the variable is expected to be. So, any questions?
Hello. Yeah, thanks. It's a great talk. It interests me greatly because we have a code base that uses quite an old hand-rolled implementation of locks. So I'm going to go back and have a look at how that works now and see what we can do to improve it. How does this compare to the locks that are built into the C++ standard these days? Like, does it take care of any of this sort of thing, or have we got to go back and do it better than the standard?
So yeah, the question was, how do these locks compare with the C++ standard implementations, or potentially, I guess, any other language implementations? So it depends on the implementation. There's multiple different sort of implementations of the C++ standard. So you get a different version on some consoles, different version on PC, different version on Linux. And a lot of the time those are using sort of the underlying implementation. So for Windows, it might be sort of a slim reader writer lock. For Linux, it might be sort of a pthread mutex. And a lot of those mean that it's got sort of this call out, and it won't be able to inline that sort of compare and exchange that it might be doing. Some of them also track a bunch of extra state there. So there might be state that sort of tracks what thread ID is acquired, the lock, or things like that. So they won't be as slim as these locks, especially if you are looking at multiple different operating systems that you're working with and you want to sort of have something that's more consistent. So you'll cut down on the memory usage that's used, because you really will only ever have 1 byte with this, and you'll also cut down on sort of the code that potentially could be inlined, because a lot of the time that C++ standard version, it just calls out to a function that exists. I know that some of the standard implementations I've looked at, you are looking at nearly 100 bytes for different implementations of a mutex. Yeah.
Given the kind of intricacies of all the different kind of architectures and operating systems and how they behave differently, what's your kind of approach to testing to make sure that there aren't any obscure edge cases with how these locks perform?
Lots of just manual testing, doing a bunch of unit tests, so really sort of saturating, doing as much sort of soak testing as you can just on different situations. And then there's a lot of little edge cases as sort of you start to sort of pull these things out, like with that strong and weak sort of compare exchange, hit sort of random situations where you might be in a situation where everything's not fully initialized, and sort of the stronger ones might sort of work in that. So there's lots of testing needed if you're really going to implement your own mutexes. There is some implementations out there that exist for sort of similar parking lot implementations that you might be able to grab online. I think there's one in Folly. I think Unreal might use similar things. There's a good blog post right up from one of the guys from Webkit on implementing some of these. Yeah. There's a lot of resources out there, but test and continue testing is the only way. I think there's another question up the front here.
For the compare and exchange failure cases that you were talking about, is there anything to look out for there? Like I think in the examples that you showed, the failure case wouldn't result in anything going crazy. But say if you swapped around the strong and the weak for the unlock versus the lock, and the weak one ended up failing, like what would you see there?
So if the lock one, if you were to change all of those to weak, you might never end up acquiring the lock. You might. So, I mean, still theoretically, when they do generate that sort of loop, the same thing could happen if there's a bunch of contention that might be happening on that cache line. But there's a lot of the time it really sort of shows up with compare and exchange, weak and strong, the differences. If you do just have something that does something once, if you're just doing a compare and exchange of, have I set this thing, do a compare and exchange weak, and you might, the result might not have been what it might have been your expected value. It just didn't change it because you did the weak version there. So a lot of the time the recommendation is just always use compare and exchange strong, and then it's only when you've got a loop that you might use the compare and exchange weak.
On the topic of testing, do you find that testing or profiling these in a vacuum gives you similar results to in practice?
Well, testing is always a hard thing. That you can do a bunch of unit tests and things like that, but in the unit test, you're typically doing something that is extremely heavy on that one mutex, and your mutexes might be scattered throughout the code base. So all of the like branch prediction and all of that's not going to be the same every time it sees a different function if they're inlined. So it's really hard to get good numbers in sort of an artificial situation, the same as what it is in a real life situation. So some of it you really need to do broad testing on it and then look at profiles of the actual game running and see how it's impacted. A lot of these things are really useful for debugging sort of situations where one of the strengths you get, and the memory reduction. The performance is really there for the uncontended case. The contention case, you're probably not going to get a huge amount of gains compared to a typical mutex. The removing of lock convoys, which is where you get that sort of ordering of mutexes, that you will potentially get some gains on platforms where it does lead to lock convoys, which I potentially should have covered in this talk. But if you watched my talk last year, I do cover lock convoys. I do so. Yeah, hopefully that answers your question. Any other?
Hi there, thanks very much. It was a great talk. Thank you very much. I was actually curious about what kind of strategies you use to actually ensure that the various things that you do to try to work around some of the potential performance limiting factors of using, platform-specific locking mechanisms or, C++ standard or other language standard approaches for locking. Particularly once you start getting into tuning it in terms of memory ordering. I know that's a particular area where it can be very easy to assume that you've got it right because fundamentally the operations being performed don't look that different. Whereas in reality, you can start getting surprising reorderings in a context that maybe doesn't look like a typical unit test, for example. And so you can end up with things in the field that are really hard to reproduce potentially. So does a lot of it just come down to just the expertise of the team to know the right calls in different places? Or do you have strategies that you use to try and catch when you get those things wrong?
Yeah, so a lot of it is expertise. There is things like thread sanitizer and that you could use. So I guess I didn't re-announce the question, but it was about memory ordering, sort of how we can best sort of test that that's the correct thing. But yeah, a lot of expertise and sort of knowledge of different things. The typical sort of recommendation, if you're not familiar with those, is just stick with sequential consistency, which is just the default. Luckily with a mutex, it is fairly well defined and fairly well understood that you're acquiring a mutex and you're releasing a mutex, and everything inside of that doesn't need to move outside of it. Things moving in, that's easy enough. So mutex is probably one of the simplest cases to sort of get an understanding of acquire and release being the correct thing. But some of those, you can even identify use cases where you might have not depended on that acquire and release correctly, and you might have some extra state. Like I've seen try acquire sort of things and stuff like that, where you introduce things that even in a standard mutex implementation, they would still fail. Also we're hitting time now, so we have to keep the question, but I can answer any other questions out in the hallway.